So we have a situation where we have a surface water treatment plant. It is operating at a flow rate of 0.5 cubic meters per second. It is dosing alum at the optimum dose that was determined in a jar test, and we're going to assume that is 12.5 milligrams per liter. So it's adding the aluminum sulfate. We'll assume that no other chemicals are being added, and we have a raw water suspended solids concentration of 87 milligrams per liter. This is extremely high, but perhaps there was a major storm event and that mixed up the sediments, and we now have this river water that we have to treat with a very high suspended solids concentration. And we want an effluent suspended solids concentration of 0.7 milligrams per liter. Just thinking about this. Okay, so we would have, just in terms of the plant, we would have some sort of screening. What's the next unit process we would have? It's a process where we want to ensure that our coagulant is evenly dispersed in the water. Exactly. So we have rapid mix, also called flash mixing, and from there we go into what unit process. So in the next unit process, what we want to do is we want to slowly mix to allow these particles to come together and to aggregate. So we want to produce bigger particles. Calculation. So we've produced bigger particles. Now, what's the next process? Sedimentation. That's where we're going to produce the sludge. And we have the clarified effluent. And typically that will go then onto filtration. And here, disinfection, storage, and pumping. So just to give you a sense of kind of how this all fits together. So we have a situation here where we have a flow rate of 0.5 cubic meters per second. That's our water flow rate. We have a coagulant dose of 2.5 milligrams per liter. We have an initial suspended solids of 87 milligrams per liter. And we have an effluent suspended solids concentration of 0.7 milligrams per liter. So let's go back and look at our, we have rapid mix. So we're adding the coagulant. Okay. We have flocculation. We have sedimentation. And we have, I'm going to call that's our effluent to the filters. So really when we're thinking about this, if I'm going to draw my system boundary, and I wanted to do a mass balance, I'm going to draw my system boundary across this entire system. So I'm actually looking at the water in, the coagulant in, the effluent out, and the sludge that I'm producing. Okay. The lines from the rapid mix to the flocculator, from the flocculator to the sedimentation basin, those arrows are all within my control volume. So when I'm actually doing a mass balance, I wouldn't even consider those. Just to give you kind of a sense of mass balance. Now, the reaction we're looking at is aluminum sulfate. And sulfate, the aluminum sulfate, has 14 waters of hydration. So water of hydration, you can think of a chemical, if you dry that chemical in an oven, it's very, very difficult to remove. You're not going to remove those 14 water molecules that are associated with each molecule of aluminum sulfate. So they're associated with it. If you kind of think about if you took Jell-O and you made a Jell-O and you left the Jell-O out in the air, it's really hard to dewater Jell-O. Okay, and it's because essentially you've got water molecules that are associated with the gelatin. So alum reacts and it forms 2 moles of aluminum hydroxide, and aluminum hydroxide has 3 waters of hydration. This is a solid. So we're going to add alum and we'll form aluminum hydroxide. I haven't balanced the equation. I will subsequently, but for now we don't need. What we need to know is how much we've added and how much aluminum hydroxide we produce, because what we're asking for is how much sludge is produced. So we added 12.5 milligrams per liter of alum. The molecular weight of alum, and that includes the waters of hydration, is 594 milligrams per millimole, and that is equal to 2.1 times 10 to the minus 2 millimoles. Now, the stoichiometric ratio for aluminum hydroxide to alum is 2:1. So that means for every 1 mole of alum we produce 2 moles of aluminum hydroxide. So in terms of aluminum hydroxide, we produce 4.2 times 10 to the minus 2 millimolar. So this is the amount of aluminum hydroxide precipitate that we would produce. So that's the amount of solid. And we're assuming here that we actually have exceeded the solubility. So we're assuming we're precipitating all of that. We're going to multiply that by the molecular weight of the aluminum hydroxide. Again, remember you need to include the waters of hydration in calculating the molecular weight. And that is 5.5 milligrams per liter. To calculate the mass of the solids, we have 5.5 milligrams per liter. We're treating 0.5 cubic meters per second of water. There are 86,400 seconds per day. It's a number that's actually useful to remember. And there are 10 to the minus 6 kilograms per milligram. And that is equal to 239 kilograms per day. So we would produce about 240 kilograms per day of solids just from precipitating the alum that we added. In terms of suspended solids, we also want to remove those. we had here 87 milligrams per liter, and we have 0.7 milligrams per liter leaving. So remember, again, you're looking at your mass balance through this system. So we have 87 minus 0.7 milligrams per liter. Again, we have 0.5 cubic meters per second. There are still 86,400 seconds in a day, and there are still 10 to the minus 6 kilograms per milligram, and this is 3,728 kilograms per day. So the total mass we produce is 239 plus 3,728. It's almost 4,000 kilograms per day of solid. Any questions? So what we've done is we've calculated this is the dry weight of solids that we would produce. Now when we add alum, and this is the full reaction, so we add alum, that releases aluminum ions, sulfate, and 14 waters. And it's these aluminum ions that react with the colloids to neutralize the surface charge, to destabilize the colloidal suspension, and to form flak. If we have sufficient alkalinity present, then what happens is these aluminum ions can also react with bicarbonate. And alkalinity in fresh waters is equal to my bicarbonate concentration plus 2 times my carbonate concentration plus my OH minus concentration minus H plus. And here your concentrations are in molar units. So, and in fresh waters, having a pH of around 6 to 8, your alkalinity is approximately equal to your bicarbonate concentration. And that's because the hydroxide and hydronium concentrations are small, as is the carbonate. So those concentrations are all much smaller than the bicarbonate, so we can say that the alkalinity is approximately equal to the bicarbonate. And here what happens then, if your aluminum ions react with bicarbonate, you produce the aluminum hydroxide that we talked about, and CO2, and the system is buffered. And if the system is buffered, what does that mean in terms of pH? So if you have a well-buffered system, what does that mean in terms of pH? So a solution with a high alkalinity is well buffered. That means that that water is able to resist a change in pH upon the addition of an acid. If it's alkalinity, when we talk about acidity, it's upon the addition of a base. So a buffered solution, again, is one that is able to resist pH change upon the addition of an acid or a base. So if you have sufficient alkalinity, you're not going to have significant changes in the pH of that water. If you have insufficient alkalinity, then what you produce is sulfuric acid, and you will have a significant decrease in the pH. So you'll have trouble controlling the pH of the system. And in a drinking water system, you don't want significant changes in the pH of your treated water because you end up with corrosion problems. We'll do this part of the problem, and then I think I'll just stop and ask questions because I don't want to start the alkalinity part. So if we have a sludge solids content, so that sludge that we're producing, that we calculated that we had roughly 4,000 kilograms, you don't produce dry sludge. You produce sludge that has a high concentration of water. And then you want to remove that water before you transport and dispose of the sludge. So we have a sludge content of 1%. That means that that sludge that you're producing is 99% water and 1% solids. So it is 1% solids and 99% water. Mostly water. The specific gravity of the sludge solids, of the actual solid itself, particles itself, is 3.01. And you're asked, what is the volume of sludge? Okay, so we produced, the dry weight that we produced was 3,968, almost 4,000 kilograms per day. We need to know the specific gravity of the sludge. And since it is 1% solids, the specific gravity of the sludge is simply weighted specific gravity of your solids and water. And water has a specific gravity of 1. So the specific gravity of the sludge is 1.02. The fraction of solids is simply the mass of my solids divided by the mass of the solids plus the water. That's the only thing we have. We're going to assume we have. And this is equal to 0.01 because we said we had 1% solids. And this is equal to 3,968 over 3,968 plus the mass of the water. And if we do the math, we calculate a mass of the water is equal to 39280. So we have almost 400,000 kilograms of water in this sludge. So the volume is equal to the total mass, so the 3,968, so the mass of the solids, plus the mass of the water, times the specific gravity that we calculated here, times the density of water, which we'll assume is, we'll just use the 1,000 kilograms per cubic meter. We're multiplying by the density of the sludge, and this gives us 404 cubic meters per day. So we would have roughly 400 cubic meters per day of sludge that we would have to treat and dispose of. So we left off on Friday with the coagulation problem, and we had stated that alum reacts with bicarbonate, forms aluminum hydroxide, and 6 CO2s. Okay. So the question is, how much alkalinity would be consumed? Now, Alkalinity it's approximately equal to the bicarbonate concentration. Exact alkalinity is equal to the bicarbonate concentration plus 2 times the carbonate concentration plus the OH minus concentration minus, so this is in most fresh waters and most of the systems that you will deal with in environmental engineering. At most of the fresh waters we deal with are between a pH of 6 to 8, and in those situations the concentrations of OH minus and H plus are negligible, and the concentration of carbonate is small compared to the concentration of bicarbonate. As you raise the pH above 8 or so, you're going to find that the carbonate concentration increases greatly, and you can't ignore carbonate in the alkalinity equation. But for the most part, we can assume that this is true. So when we're looking at this equation, we can then look at the stoichiometry, okay, and I just realized I missed a 6 there. So for every 1 mole of alum that we add, we're going to consume 6 moles of bicarbonate, or 6 moles. So we previously calculated that we were adding 2.1 times 10 to the minus 2 millimoles of alum. And if we multiply that by 6 millimoles of bicarbonate for every 1 millimole of alum, so that's just the stoichiometric ratio, and that is, now alkalinity is usually reported not in millimoles, but it's reported in equivalents or in milligrams per liter as calcium carbonate. So we need to convert this to milligrams per liter as calcium carbonate in order to obtain the traditional units that are used in environmental engineering. So we have 1.26 times 10 to the minus 1 and 0.126 millimoles per liter of bicarbonate. Bicarbonate, we can typically use the charge. There are 1 milliequivalents per 1 millimole for bicarbonate. That's true for bicarbonate. For carbonate, it's actually 2, and that's this 2 here is actually 2 milliequivalents per millimole, or actually equivalents per mole. So we can write this down as 1.26 times 10 to the minus 1 milliequivalents per liter of bicarbonate. And then the last set of calculations, we have 1.26 times 10 to the minus 1 milliequivalents per liter. It's our bicarbonate concentration. There are 50 milligrams per milliequivalent of calcium carbonate. There is a video that I produced actually for 480 on hardness and alkalinity. It's on YouTube. It's on the YouTube channel, on my YouTube channel, that actually goes through all of these calculations in much more detail. So if you haven't done these types of calculations in a while, you don't remember this from 280, that video's there. You might want to take a look at it. There's also another video that I can provide from a colleague that also essentially has done the same types of calculations. So what this says, and is we would consume, by the addition of the alum at 12.5 milligrams per liter of alum is going to consume 6.3 milligrams per liter as calcium carbonate. So that is the amount of alkalinity. So this is our delta alkalinity, the amount of alkalinity that's consumed. I added a page in there and I didn't need it. Okay, so what I want to do now is we're going to move on to rapid mix. So we've looked then at how do we determine alum doses. We've looked at the reaction of alums. Now we really want to look into the design aspects. The question was, how do we get the 50 milligrams per liter? So calcium carbonate has a molecular weight of 100 milligrams per millimole. Calcium is 2 plus, carbonate is 2 minus. So the number of equivalents per mole is 2. We can just use the charge. It's more complicated than that, but for the most part, for most systems, you can simply use the charge on the ion that you're looking at. So N is equal to 2. That's 2 milliequivalents per mole, per millimole. So for every millimole of calcium, it is 2 milliequivalents. So equivalents of charge is really what we're thinking of. So if we take this 100 milligrams per millimole, we have 2 milliequivalents per millimole. Millimoles cancel, or if we did this in moles, it wouldn't matter. So that gives us 50 milligrams per milliequivalent. This is the equivalent weight of calcium carbonate. So when we're converting from milligrams, we can convert from milligrams per liter as the ion to milligrams per liter as calcium carbonate. We'll use the equivalent weight of calcium carbonate. And that's critical because when we look at, for instance, when we look at hardness, everything, all of our measurements, all of our recording is always as milligrams per liter as calcium carbonate. Those of you in 480 that have been measuring alkalinity and hardness have probably noticed that the calibration data that you're given, your concentrations are in milligrams per liter as calcium carbonate. And that's what you'll report. And this is what we traditionally use. We use this for alkalinity. We use it for hardness. So we will use it in a number of cases. And we use it in terms of review. Alkalinity is the buffering capacity of a water. So it's the ability of a water to resist a change in pH upon the addition of an acid. And when we talk about acidity, here we're looking at addition of an acid. With alkalinity, we're looking at that change in pH, the ability to resist a change in pH upon the addition of a base. So that's the difference between alkalinity and acidity.